Hello. So this lesson is about the extreme values, or the extreme values of functions. We're really going to be talking about more or less the high points and low points of functions, so as they oscillate a little bit. So here's an example of just a picture of a function that we're calling f, and notice that this function f is defined on a closed window from a to b. So we have this restriction that the function is defined here. It's also continuous on this window. So what you'll notice, if we're talking about extreme values, is we're going to want to be able to identify the highest point and lowest point of this function. So we can see the lowest point, or the lowest y value, would occur over here on the left. So this is where we have f of a. So we can document these locations here. So right here, we have f of a. So f of a here is really our absolute minimum. It is the lowest point. So we could keep track of these values here. So f of a, you can see this is the lowest point on the graph. And then if you want to find the highest point, that's not really identified here, but you can see it right at this location. So we'll identify it now, we'll label it. So you could call this C, for example. So when we think of the highest point, we're again thinking of y values. So we can go over here, and so this is f of c, the y value, and that appears to be the largest value. So we have f of c. So notice one more location where we have a low point, but it's not the lowest one, is right at this location. So we can identify that as well. So I'm just going through the alphabet here. We can call this D. So this point right here, f of D. So you can see f of D falls in between these two extremes. So f of d would not be considered an absolute min or an absolute max, but we might use the term this is a local minimum because it is a low point as long as we stay very, very close to d. So this is also a point of interest. Okay, so this is just a diagram saying that if you have a function defined on a closed window and it's continuous, it's definitely going to reach a highest point and it's going to reach a lowest point. So this is made formal in a theorem here, and I'll just highlight it right here. So this is called the extreme value theorem. And extreme values, as you could guess or predict, they speak to the high points and the low points. So if you have a continuous function, f of x, on a closed interval, and our closed interval here was a to b, then that means the function is guaranteed to attain both an absolute minimum and an absolute maximum. So if you look at the example that we just went through, we were able to identify f of c as the absolute maximum, and then f of a as the absolute minimum. Okay, so the next thing we're going to go through, this is an important definition that's going to lead directly into finding these things, the high points and the low points. So I'm going to put the definition right here. So this here is the mathematical definition of a critical number. Okay, so the critical number that we're going to talk about here is going to be x equals c. So the first assumption, and this is an important one, is that the y value must exist at that point. So f of c exists. And then if you want to talk about a critical number to a function, one of two things occurs. So they're listed here. So this says f prime of c is equal to 0, or f prime of c cannot be calculated. So really it's a fork in the road. So it's saying if your derivative is equal to 0, or if the derivative can't be calculated, then that means this number is special. So we call x equals c a critical number to the function. So I want to talk about each of these two cases, so this way we can think about why these two conditions exist. So we'll draw a quick little picture here. Okay, so f prime of c equaling 0, we saw this earlier. So this means we have a horizontal tangent. So if you look at this diagram, this is saying when we get close to c, f prime at c the function is really not changing at that point. Right, so f prime of c is equal to 0. So we have a horizontal tangent there. So this definition says that this number, c, is a point of interest, right? It's something that we should look at. The other condition here is the derivative is not defined. So we could look at another diagram here. And we've seen this also. So in this case, we'll call this f. And so we have a sharp turn here. We'll call that c. So notice if you look at this location, f prime of c, so this here cannot be calculated. You could say f prime of c does not exist because the tangent line is ambiguous at that location. Okay, so according to this definition, what it's saying is if either of these conditions occurs, then that means the number x equals c is one that you should examine. So it's an important number to look at. And you can probably see why we would call this a critical number. So in each of the diagrams you can tell if you look at the function that they, at the location x equals c, we're talking about an extreme value. So if you look at the first picture, you can see at x equals c, this is a valley to the graph. So this speaks to the minimum value on the graph. And at this, in this diagram here where the derivative failed to exist, it actually speaks to the maximum value of the function. So the reason we talk about these critical numbers is they lead directly to the extreme values of the function. So in some sense what we do in this lesson is we're going to deal with functions, we're going to identify the critical numbers to the functions, and then see if we can locate the high points and the low points. Alright, so we're going to go through an actual example here. See if we can identify the critical numbers and then just identify the extreme values. So this is the one that we'll go through and talk about. It's a pretty straightforward example. So this problem is saying let's find the absolute extreme values. So let's find the highest point and the lowest point to this function. It's a pretty simple function, and notice this is the interval of interest, right? So on the interval -1/2 to 4. So when you come back and think of the extreme value theorem, remember that that theorem guarantees that you're going to have a high point and a low point as long as you have a continuous function on a closed interval, -1/2 to 4 in this case. So the basic idea is we're going to find the critical numbers here and assemble them all, and then just check them on a table to see if we have found the high point and the low point. So I'm going to jot down the function here. This is a pretty simple one. Okay, and then the interval of interest here. So -1/2 to 4. So even though this function is defined well beyond this range here, we're just going to examine this particular window, -0.5 to 4. So to find the critical numbers, we have to differentiate this function and figure out where is it undefined or where is it equal to 0. So this is the fairly simple part. So we find the derivative using our basic rules. So 3x squared minus 6x. And then what we can do here is just to factor and simplify. So I'll pull out 3x, and we're left with x minus 2. Okay, so this is where the fork is in the road, because the critical number definition says figure out where your derivative is equal to 0 or where it's not defined. So we're going to think about both of these here. We're going to think where is the derivative equal to 0 and where is it not defined. So we're going to set up both of those problems. Whatever we get out of doing that, that will give us exactly the critical numbers to this f. Okay, so the first part here, setting it to 0, this is pretty easy to do. So taking the derivative and setting this right equal to 0. So if x is 0 or 2, then this equation will be valid. So we gather these two here. So these are right away going to be critical numbers to the function f. So these are definitely numbers to check. And what we learned from talking about the earlier stuff is these are going to lead to potential mins or maxes, so high points or low points to the function. So the second condition, checking to see where is this not defined, well, notice for any value of x that you use here, you will have some value that comes out. So this second condition is not going to apply in this case. Another way of thinking about this, where is the derivative not defined? Where do you have vertical tangents or cusps in the graph? So if you think back to the function here, we are dealing with a nice, smooth polynomial function. So this function is differentiable everywhere, so this condition is something that can be tossed out. So in some cases, you might get a critical number out of this condition and maybe not out of that one, or vice versa. In this case, the only part that applied was setting the derivative equal to 0, and then we end up with two critical numbers that come out. So to finish the problem like this, all we really have to do is to test these two numbers and to plug them into the function and to see which one is going to give us the highest value and which one is the lowest value. Something else that is really important is we should check the a and the b, right, on the window that is provided, because you never know when your function might be taking off at one of these endpoints, because you might have your largest or smallest value occur at those points. So what you should end up doing is to make a table that includes your critical numbers and then also your a and your b. So I've done this for you to speed up the process here, and this is really pretty basic math. So we're going to make an x column and a y column, right? X and f of x. And notice 0 and 2 are included here, and then also your a and your b, -1/2 and 4. And so you simply take these four values, insert them right into your function, right? Not into your derivative, but into the function itself, and then you just calculate the outputs. And then from here, you should be able to find your highest point and your lowest point. Alright, so looking at the table, if you're just glancing at the table, the mins and the maxes come from the height of the function, so you're really looking at the y column. So you can definitely see the minimum is going to occur right here, because this is the only negative value on this entire y column. Right, so your absolute min is going to occur there. Okay, so your absolute minimum is -3, and it occurs when x is equal to 2. And then your largest value is the last one, that's the 17. So that's your absolute max. Right, and you can probably see the importance of checking the boundary point, right? Checking the b equals 4, because it turns out this function is one example where as you test close to the boundary or at the boundary, you get your largest value by far. So this is your absolute maximum. So you can definitely see an illustration of the extreme value theorem that this function is continuous on the closed window, so there will be a smallest y and a largest y. So something we should do in addition to looking at this table is thinking about this graphically, because oftentimes a graph helps everything make sense. So if you think about this function, x cubed minus 3x squared plus 1, you could graph the function on a window like this, but looking at the graph of this function, you can't really see this information in the graph, because this is just a random window here. So the best thing to do is to pick the window of examination, -1/2 to 4, and then you should be able to see these characteristics right in the graph. So I'm going to show that here, and then maybe mark up the graph just a little bit so we can see what's happening. So now if you look at this graph, this one is exactly a graph on the given window, from -1/2 to 4. So I'll repeat that here. So this is the window of interest. So if you look at this graph, this is in fact the same as the previous graph that I showed, but this is the window of relevance from -0.5 to 4. So we can highlight the endpoints so we can see what is happening here, like this. And then you might want to highlight a couple of values so you could see a relative max there, and then also a valley in the graph right here. So if you look at this graph, I think something that stands out is right away you can see the importance of checking the boundary, of checking x equals 4, because at 4 you can see the graph by far has the largest value of 17. That's why we ended up with the absolute maximum at that location. And then the absolute minimum value occurred at 2, and that's also pretty visible from the graph because this is the only point where the graph goes negative. So the lowest value, -3, occurs when x equals 2. So the interesting mix here is that we do get our extreme values, our min and our maxes. Notice one of them occurred at a critical number, x equals 2, and then the other one occurs at the boundary point. So in summary, you just take your function here and get all of the critical numbers, and then test those critical numbers with the endpoints a and b, and then just look for your largest and smallest y.